Good evening, everybody. Let's start by what is steer-by-wire, some key features of the components. Steer-by-wire means electronic steering system that can be, that will replace the mechanical linkage between the electronic control and improve precision and flexibility. It's been used since a while, since a few years for the rear axle steering system, and now it's becoming more and more a reality also for front axle steering systems. Such a system provides an adaptive and customized handling, thanks to the fact that the variable steering ratio can be applied. Road noise isolation is guaranteed by this no mechanical linkage between the steering wheel and the steering system. And the integration with ADAS is straightforward. Increase in safety and redundancy. All the systems are provided with a redundancy system, including fail-safe mechanism and backup system for enhanced reliability. And this is the only way to handle autonomous vehicles that facilitate precise electronic control and support self-driving technologies. How to develop a steering-by-wire system? Following probably the natural V cycle will be too long. Thanks to the increased capability of real-time simulations and driving simulators, we can maybe stretch those development cycles and make sure that starting with a proper model in the loop, then as soon as hardware becomes available, and any time can be replaced by hardware in the loop and also a mix of model, software, and hardware in the loop to achieve the goal of calibration, development, calibration, and fine-tuning of the system. Starting from model in the loop, the two main application areas are offline applications and online. One mean offline is simulations without a driver in the loop. One mean online on the driving simulators to have the first human factor and the human feedbacks that my colleagues Tom and BJ will express later on. The further step is then to evolve from model to software and hardware in the loop. What is the main goal of having software and hardware in the loop in conjunction to a driving simulator? First of all, is the main development of the software and the hardware itself. The calibration and validation capabilities in order to have to validate all the functionalities of the steering system, and finally the human factor for start early calibration on driving simulators before the first prototype vehicles are available. To do so, there are two main key aspects on real-time simulation and driving simulator. First of all is the real-time platform. Together with concurrent real-time, we develop a state-of-the-art real-time platform able to serve any sort of real-time simulations with or without a driver in the loop. We have a huge variety of systems starting from 8-core up to 16-core system with a single or dual CPU. Those systems are based on the latest technology of Xeon Gold, 5th and 6th generation, as well also the brand new Auto 24 Extreme with 24 cores, 8-core at 5 gigahertz and 16-core at 4 gigahertz. The second key pillar of real-time simulation is the ability to have a real-time ecosystem valid for every stage of the development cycle. Thanks to the VI-grade software ecosystem, we are able to guarantee any possible linkage to third-party software, as well also to stress the utilize VI-grade toolchain for vehicle dynamics, for visuals, scenarios, building other scenarios, attach controllers like ECUs and external devices, as well also managing tire models and complex tire models for tire design. I would like now to hand over to Tom that will go deeper in discussion with the steering solution.
Thanks, Alessandro. So I'll just give you a little bit about Chassis Autonomy. So we're a startup 3.5 years old. We spun out of a Swedish OEM in October 21, headquartered in Trollhättan in the west coast of Sweden with a smaller division in the United Kingdom. Fundamentally, we design and develop steer-by-wire. We design it from the ground up. So as a startup, we're uncompromised by legacy. So we're not constrained by global facilities that manufacture conventional EPS systems in the millions. That enables us to kind of design with a blank sheet of paper and design from the ground up. If we were to reimagine a steering system for tomorrow, one that doesn't have the mechanical connection, one that is steer by wire, we would do it differently. And that's what we've done at Chassis Autonomy. So we no longer have a rack and pinion. Rack and pinion facilitates a mechanical connection to a steering wheel. By definition, we don't need one. We don't have a rack and pinion. We call our steering system, it has a steering shaft, not a steering rack. Alternative solutions, we also have the conventional and well-known parallel axis power pack. So again, we eliminate that, we eliminate the drive belt, and we run with concentric direct drive. Again, we're looking to reimagine the steering system of tomorrow, and we're looking at different requirements, looking at potentially higher requirements for durability, higher requirements for load, and we're looking into fail operational performance. We're eliminating all single point failure modes to ensure that we have steering functionality, even if we get one failure across the system. As a startup, whilst we're unconstrained by legacy, we still may have some development gaps that we need to fill, and this is really where the partnership with CAE Value and VI-grade comes into play. So when we're developing our systems, we know that we need to be fast to market, we need to develop the technology, we need to develop requirements in some cases. And so by using simulation-driven development, we're using hardware in the loop rigs, we're using driver in the loop, we can really start to fill potential requirements gaps from our customers to make sure that we can develop specifically for those requirements. So we're looking into durability cycles, we're looking into drive cycles, abuse loads. We can evaluate these loads, we can develop them, we can define what those specific loads are for the specific use case for the specific customer, and that allows us to develop again and optimize the systems for the future autonomous vehicles and highly automated vehicles. We're called Chassis Autonomy because our original concept was developed again for autonomous vehicles. So we're looking into vehicles which have requirements for 1 million kilometers rather than conventional 300,000. We're looking at potentially heavy vehicles, 5-ton people shuttles, 25 kilonewtons rather 18 to 20 for conventional passenger vehicles. So that's our primary market, but we've also got a lot of activity, a number of projects ongoing to develop for level 3. So that's when we're looking into human-driven steer-by-wire, as we call it. We're looking into deploying a road wheel actuator with a hand wheel actuator, and this brings a different level of requirement. Again, we're looking to focus on steering feel to ensure that the driving experience remains as it is with an EPS system or even those systems that went before it. So again, when we're looking at developing the systems for those two distinct sectors, we've got human-driven steer-by-wire. Again, we're really focusing on steering feel. So just as hydraulic power steering systems were replaced by electric power steering systems, the key requirement was to maintain steering feel. When we move from mechanically connected system to a by-wire system, again, we're looking to now not only maintain a steering level of performance and comfort and feel, but we're actually looking to replicate what's happening at the road wheel actuator on the hand wheel to ensure the driver has comfort and also has that feeling of safety. With steer-by-wire, we open up a lot of different features and functions to enhance comfort and vehicle dynamics. Again, infinitely variable steering ratios. We can do different things when drivers are potentially doing activities on the steering wheel which may not be perfect for the road wheel actuator, potentially curb pushaways. We can kind of have different responses to those systems. When we're looking into level 3 and level 2 systems, obviously there's a transition from the vehicle operating in automated mode and going back to level 2 where the human driver is responsible. So with driver in the loop, we can really use that system and the simulation environment to assess those functions, those use cases, and develop suitable responses for that. And that's really fundamental. We can do a number of iterations in hours, let alone if we're on a track with a vehicle, it would take days. So really accelerating the development of steer-by-wire systems. When we move to autonomous shuttles, it's a very different use case. So we've got the road wheel actuator. We no longer have the human driver in the loop. So we don't have to design for steering feel. but we have different requirements. So we're often working with new platform developers, new vehicles, new use cases, new operational design domains. So we're looking into potentially a new area of operating vehicles. We often lack 100% of the requirements. So again, we can use offline, driver in the loop, sometimes mostly hardware in the loop, to really establish reference duty cycles, reference operating envelopes, and make sure that we're developing the steering system for the specific needs and requirements of that vehicle. And really, again, autonomous shuttles, a core market we're seeing is 5-ton shuttles, extended durability, 1 million kilometers higher loads. So we can, again, use the simulation environment to establish those relevant test and development cycles, and we can run our systems hardware in the loop to validate them. I'll now hand over to VJ.
Thank you, Tom, and a very good afternoon to all of you tuning in. Now, how can you talk about steer-by-wire without thinking about system safety? Yes, the design freedom offered by variable steer ratio is very exciting, the disturbance isolation, but the priority should always be safety first. Now, I'll take you through some key concepts in system safety, and these are simple definitions, so hopefully you can keep them in mind when we do a deep dive on this later. So typically a system safety process starts with something called a hazard and risk assessment. And this is where engineers and stakeholders sit together and identify different risks and hazards, and also define mitigation strategies. Now, controllability is defined as the ability of a vehicle to avert a certain disaster or damage through timely action. Availability is a characteristic of a system that aims to ensure a certain operational functionality. Degradation, this is pretty straightforward. It's a state of reduced system functionality. Transition, also straightforward. Is when you go from a normal state to a degraded state, or between one degraded state to another degraded state. Now, the degradation concept is the strategy that you use to handle these transitions and degradations, but also ensure some system availability while you handle those transitions. Now, whether you're developing an L3 or LL4 or something perhaps in between, your requirements are going to be quite dynamic, or sometimes maybe conflicting. The vehicle architectures might be quite complex now. And if you want to keep pace with the current market, given all the technological advancements, you cannot afford to sit around and wait to build a physical prototype and then do your safety and performance evaluations. What you'll have to do is something called front loading. So front load a lot of the decision-making process to a virtual development ecosystem. And you want a development process that is fast and flexible, also safe and sustainable. Now, I know some of you in the audience are very familiar with this type of working already, but for the sake of the general audience, I will take you through this typical workflow. So here you have a workflow from the end customer all the way down to the tire manufacturer with the system suppliers in between. So the typical workflow would be the end customer would have an OEM works together with the tire manufacturer in what is called a virtual tire loop. And then they test different iterations of a tire, and then once they are satisfied with a particular status at a certain phase of a project, they then share that vehicle model plus tire model with the system supplier, who then uses that as a reference model to develop their system models, functions, fine-tune and calibrate things, and share back the system models. You can also share it with the possibility to tune some of the parameters, some calibration possibilities, especially if the OEMs have access to, let's say, a driving simulator. You can do a bunch of work way before you build a physical prototype. So you can work on ADAS AD function development. Is my function interfering too much? Is it interfering too little? Is it too aggressive? You can, of course, do a lot of steering feel parameter tuning. You can do the tuning, variable ratio tuning, depending on the speed. And of course, how can you forget HMI, which is extremely crucial nowadays. You can also work on fault injection. So if you look at a conventional steering system, if you look at this conventional process as of today, this rectangle that you see here within the dashed lines, that used to be handled by a single supplier. Now there is no mechanical connection between the hand wheel actuator and the road wheel actuator. So now this opens up space for different combinations of suppliers, and it will be an interesting dynamic when it comes to integration, make sure the integrations happen correctly. Now, of course, you cannot assume every supplier or every company is using the same software. And this is where the third-party compatibility of VI-grade ecosystem played a very crucial role in chassis autonomy, going for this VI-grade ecosystem and a driving simulator from VI-grade. So as Alessandro mentioned before, all the way from vehicle model to tire model to controllers, there is third-party compatibility with the common players. And here's an overview of the chassis autonomy driving simulator. It's a VI-grade customized desktop static simulator. But the key difference I would like to point out is the active feedback motor here that you see in the corner. This is the same feedback motor. It's a high-end feedback motor with tunable parameters like in the slides Alessandro showed. And this is the same feedback motor that is available in the VI-grade dynamic and motion simulators. So this is a really crucial decision for chassis autonomy, because whatever method development that you do, you can do a lot of the engineering work in the static rig. And then once you're ready, you can take the methods and models to a dynamic simulator in one of the OEMs and get quick feedback and work more in a collaborative way with the OEM. It's powered by the Authawk 32, which is extremely powerful, hard real-time capable. It can run real-time multi-body models and physical tire models, which can come into play depending on the road inputs. The graphic environment is VI World Sim, which is Unreal Engine powered. And one of the key features was we got access to the VI-grade virtual proving ground. This comes with handling track, ride surfaces, and different rally tracks, for example. And this has proven invaluable for us because most OEMs, they have their own test tracks. So they do a digital scan of the test track and then use them in their virtual development process. But this is the virtual proving ground has been a really excellent asset for us. If you look to the back of this cabinet, you can see an interface to different protocols, CAN, LIN, EtherCAT, and UDP. So this can help you connect different hardware in the loop rigs, or also even different alternate devices, for example. Now let's go back to system safety. I know it's a little bit maybe late in the afternoon, but let's try to do a thought exercise. So let's say you're in a steer-by-wire vehicle. You are in normal mode, nothing is fine, enjoying the drive or enjoying the ride or whatever it is. And then there is, let's say, a system warning that says it has to take you to a restricted degradation level D1. Perhaps it's a reversible fault, a temporary fault. Maybe it's a temporary drop in voltage of your system. But you can still operate the system at, let's say, 75 to 80% operation. And so you will have to work out how you handle such a reversible fault. Maybe you opt for strategy A, where you go from normal to D1, and then after a while go back to normal operation. But sometimes the fault could be a major one, and then you will have to use a strategy B, and then where you have to go from normal mode to something called limp home mode, where you are expected to have the vehicle at a velocity less than 10 kilometers per hour. So how do you handle such a transition? You will need a link to the speed reduction controller. You also need to handle different states of the vehicle. And while you're heading to D2, maybe there is another fault, which is really critical. And you might end up having to bring your vehicle to a safe standstill now, or a minimum risk maneuver, as they call it, because what is safe can be a little bit subjective. Now, how will you evaluate all these transition strategies, degradation modes? You cannot do that optimally in a test track with physical prototypes. Now, keep in mind, you have to do this in different scenarios as well. It's are you in a highway doing a lane change? Are you entering a highway? Are you exiting a highway? Are you in a pedestrian zone? So the library of use cases is ever expanding. The system safety standards actually allow for additional lateral guidance in case of problems. So they also allow for the system to have rear axle steering, or also something called steer by braking. Now, if you're a vehicle architect, let's say you decide, I want rear axle steering in every future vehicle. How is that going to look in terms of cost? It's a good choice, but maybe it's not going to fit the market in terms of pricing. Okay, can you do what is known as steer by braking? What you do there is single-sided braking to induce a lateral displacement of the vehicle. Yeah, that's it's a good option as well, but how well does it work when you're transitioning? At high speeds, it works well, perhaps, but when you're in medium to low speeds, you will have to take a judgment call. Do you have to maybe adjust a certain suspension parameter? Maybe you have to change your design requirements from what it was conventionally. But if you do that, how is that going to affect another performance metric? So this is the thing. When it comes to optimization, it will end up being a multi-attribute, multidisciplinary optimization between durability, safety, vehicle performance, and this causes an interesting dynamic. Now, what are the expectations from these steer-by-wire standards? So the standards expect that the assessment of controllability, remember the definition from before, the ability of a vehicle to avert a certain disaster through timely action. So the controllability assessment must take the form of a subjective evaluation by expert drivers. You should also be able to extract objective KPIs and metrics before fault injection and after fault injection. And you have to reassess controllability during all your transition strategies and degradation modes to determine a safe system response. So what are the implications of this? So let's say you are a simulation person, or you are a test environment together with simulators and hardware in the loop rigs. You're in a test lab responsible. It means your test case for verification and validation is going to be considerably bigger. So it's going to be a lot of workload coming your way. You could argue, okay, I will do my fault insertion checks and extract metrics offline, but can you simulate driver reaction in your offline background scripts? Perhaps it's not so easy. And this is where driver in the loop simulators come into play, is where you can capture early driver reaction and also things like fault tolerant time intervals, maximum permissible latency evaluations. And who knows, perhaps in the future we will have to end up doing something called psychological safety assessment, maybe put a passenger in the loop in some sort of a simulated environment or a simulator, where you take them through these critical scenarios and actually assess how safe do they feel when they are in this kind of safety critical scenario. Is the HMI informing them the things they need to be informed with? Is my system handling the transition safely? Now, let's put some practical applications of whatever we discussed, because now, as you saw in the previous slide, based on the expectations from the standards, you have to bridge the objective and subjective. Now, how do you do that seamlessly? So you have to go from model in the loop to driver in the loop in a smooth way. So let's say you have a scenario. Let's say in this case, it's a sign steer maneuver. Let's say when it comes to these lateral situations, a typical KPI is the vehicle yaw rate or lateral acceleration. So you have to extract the behavior before the fault and after the fault. And subjectively, you need to rate from easily controllable to impossible to control. As you can see in the plot there, yeah, apologies for the graphics, but it's a plot of the yaw rate against time for a sign steer maneuver. It could be any other maneuver, slalom, or anything else for that matter. And the red line that you see is the behavior, is the fault injection. So the line to the left, to the plot to the left of it is before the fault, and after it is to the right is after the fault. So you can come up with a metric like, okay, I will take the mean of the maxima before the fault and compare it to the mean of the maxima after the fault, and then develop your requirements and metrics objectively in that way. But then you will have to run this scenario subjectively in a driving simulator, and that would be a much safer way to do it rather than injecting faults in your physical prototype where you are not sure how the system will behave. So this way, you can also teach the drivers who are going to do these final assessments to how to do the maneuver, and they can follow the standards and maneuver instructions before they enter the test track. So how do you go about doing this? So let's say you have a system model. In this case, it's a chassis autonomy road wheel actuator, for example. It's very easy to connect to a vehicle model that you get from an OEM, and you can run this simulation pretty easily through Simulink. And then how do you take it to a simulator? So it's pretty easy. So you take your system model, replace the interfaces with something known as a real-time database blocks. So you're making the system model simulator ready. And then you compile your model into the driving simulator. So this gives you a pretty seamless process, in my opinion. And you can see the driving simulator in action here. It's not the fault injection scenario that I explained right now, because we are not in a position to show that due to confidentiality, but it's let's say a simulation or a driving scenario of where I'm extracting steering feel on center curves. So as you can see, my colleague is pushing the car, giving it some steering inputs, and you can see a green plot dynamically moving around. Again, apologies, it's not clearly visible, but what I'm plotting there is a steering feel on center curves. So those who are familiar with vehicle dynamics in the audience, they know it's the steering wheel torque versus angle, torque versus lateral acceleration plots. And I've also plotted some rack forces there. So you can monitor your KPI in real time, and specifically when it comes to variable steering ratio, this is where it's very powerful. You can do very early calibration work, and you can log multiple vehicle metrics. And this is what makes a driver in the loop simulator the perfect collaboration platform between your testing engineers and also the simulation engineers. If you are maybe working towards an autonomous driving customer, maybe a robotaxi customer, what you can do is send out your vehicle model on something called a data drive or a synthetic data exploration. So what these robotaxi players do is they have something called they operate in a specific environment called ODD, operational design domain. So if you can get hold of this ODD, what you can do is optimize your control algorithms, you can optimize your actuator motions for that specific ODD. So maybe it's an ODD where you're mainly doing highway driving, merging exits, or maybe it's a combination of highway and very low speed pedestrian areas. So you can do this multi-attribute optimization based on safety, durability, performance, and on the depending on the ODD that is available. Now, XiL is not plug and play. It's an evolutionary process. It's not something that is just going to happen overnight. So like Alessandro mentioned, typically you start with model in the loop. This is a phase where you don't have too many software components, and it's very useful to do concept studies, work out early requirements, understand purely how your function works. You can do it offline and also in the online world once you compile your model. The stage after that, the next step would be to bring in your software components. So you have the plant model together with the virtual ECU or an S function. Of course, you need to check everything works offline. Make sure you do that, please, because otherwise you will have some flags not working or something that is very silly that is not working. Then you integrate this VECU, virtual ECU, into your driving simulator to do more detailed evaluations, fault injection, latency delay studies, etc. A focus for chassis autonomy is mainly a road wheel actuator. But let's say if there is a partner who is coming in with a hand wheel actuator, they can follow a similar development process and come to a meeting point where you do an integration of both models and evaluate them in the simulator, and then take the next stage to connect the simulator to different hardware in the loop rigs or any existing rigs. So following this methodology will, on paper, should lead you to a safe release of a vehicle, a very efficient development process, and happy engineers and stakeholders. Now, I will have to warn you that do not forget to do regular correlation loops with measurement data, with your vehicle data, and that's how you bring the maturity levels of your models up. You identify mistakes, catch them early, and this is an iterative process. Now, with that, I hand over the ball back to Alessandro.
Thank you, Vijay. So, as Vijay said, it's an important stage is to also connect mechanically on test rigs and driving simulator and real-time simulation. And here, thanks to the strategic partnership we raised with two major players, Hem Dynamics and Mechanical 42, we are able to supply turnkey solutions for EPS test rigs, also for steering-by-wire technologies. First, with the M Dynamics, we have a very compact system, especially for the option 1 with 16 kilonewton of peak force and continuous force of 8 kilonewton. The system can be, of course, upgraded for also traditional steering system, but in terms of the major differentiator is the fact that we use a single tie rod linear actuator and compensate the absence of the second tie rod actuator. Everything is connected through Ethercat communication to the real-time system. So it's possible to run real-time simulation offline with a virtual driver or connected to a driving simulator. The other option, it's with Mechanical 42, where the concept is to apply the exact tie rod force on each tie rod. So we have 2 actuators. We can manage up to 20 kilonewton per tie rod as a peak force. We also have 2 axes of motion, X and Y or Y and Z. We can also reach a max linear velocity of 1 meter per second. And of course, it's a larger machine, and same also for the one from M Dynamics. The system can be then upgraded for traditional steering systems. But both systems, what is most important part is how they are connected to a real-time simulation station and driving simulators. Here, the architecture schematics you can see the real-time machine is at the core of the simulation, where everything it runs. So the vehicle model, the real-time model, runs on the real-time system. Through the help of I/O boards, there is also a possibility to directly connect and manage the ECU of the steering system, of the EPS. So they are also live streamed with the proper protocol. That will be CAN or CANFD lately, or even the future automotive Ethernet. The test rig and the driving simulator exchange signals through the steering system here. So the actual steering wheel will send the steering angle, the steering velocity, the rec force for aerodynamics, or the tire rod forces for the mechanical fortitude, and the vehicle speed. And we receive the back from the test rig. There, of course, we emulated the road conditions and we applied the exact force coming to the wheel, and from the wheel to the suspension and also to the steering, the steering torque and the rec displacement. All these is in closed loop, real-time closed loop with the lowest latencies possible. And this applies, as Vijay said, to any sort of VI-grade simulators, from compact or customized desktop, as Vijay mentioned before, with the active steering system from VI-grade, then the compact, the static, and the dynamic simulators from 6 degrees of freedom to 9 degrees of freedom, from the small to the largest platforms. This will end the presentation of today, and we're now ready for Q&A. Thank you.